Okay, so today we're going to start chapter 4. I've got some good news and I've got some bad news. Which one do you want first? Bad news. So remember, in chapters 1 through 3 where I kept saying, no, you don't need to simplify that. No, don't simplify that, just leave it. We'll deal with that later.
Now is later?
Now is later, correct. So we're gonna have to start working on how to factor some of those big scary derivatives, but we'll deal with that later.
Now.
The good news is, I think you're gonna find this chapter considerably easier than chapter 3, because as I mentioned earlier, it's very algorithmic. By algorithmic, I mean, here's the steps to follow, do it, everything is great. Okay. But we'll see, maybe not. All right, so we're going to talk today about maximum and minimum values in a function. We're going to deal with something called extrema. And we're going to talk about the difference in extrema. We've got relative extrema, and we've got absolute extrema. We're going to find some critical numbers. And then most importantly, you should be able to snap your fingers. Yes? Anybody not? Would you admit it if you couldn't? No. Okay, just checking. Okay, here we go. This is the part, let me start over. This is part of the graph of x cubed minus 2x. Angelina, what points on that graph do you find interesting, and why? Oh, that's not a good way to start an answer. None of those points on that graph you find interesting? Not a single one. Of the infinite points on that graph, none of them are interesting to you. Wow. Weak sauce. Sam, what do you like?
Negative. The I don't know, I forgot what they're called.
You could just point.
These two.
For the sake of the video, Sam is pointing to the top curve and the bottom curve.
Yeah.
What are those called? Sam? What would you call them, Sam? When you're showing your little brother, little sister? Neighborhood kids, little neighborhood, that would be creepy, never mind. You're explaining to somebody who doesn't have calculus what you were talking about when you were on the video. What would you tell them those locations are on that curve?
The maximum and minimum values.
Ooh, interesting. Okay, beautiful. Charlie, what points do you find interesting other than the two that Sam already pointed out?
I like 0, 0.
Why?
Because it's 0, 0.
Oh, also known as?
The origin.
Good. Are there any other points on that graph, Charlie, that you could lump in with the origin as being interesting?
The x-intercept.
Ooh, excellent. Where would those be located, approximately? He'll get there eventually. He's a smart fella.
1.3.
Okay, and?
Negative 1.
Excellent. Now, Charlie referred to those. Charlie referred to those as the x-intercepts. What else would those points be known as, Jack?
Solutions.
Solutions. What else would those points be known as, Jack? Questlove is part of a group named the... Questlove is part of a group called the... Let him stew for a second, hold on.
I can't deflate.
Valid.
The roots?
The roots, good.
I knew this.
Those are x-intercepts. Those are roots. Those are solutions. And last but not least, they're also known as zeros. Thank you, Sophia. Excellent. Okay. Beautiful. Luca, how are we feeling about that dot on the bottom there? What's special about that point?
It's weird.
Okay, good. Yeah, I deal with that all day long. That's how I start a lot of meetings about students. So, Mr. Reedy, how do you feel about student A? They're weird.
I don't know.
And then they always say, what I just said, what else is interesting about them? And then what I'm not allowed to say is, I don't know.
Yeah.
You know, because I spend 80 minutes a day, every other day with them. Just being weird is not enough to, you know,
I
set.
break the rule. I don't know.
Okay. Nothing else interesting about that point? Any? Malik, what do you got? Oh, don't be such a coward. What?
I mean, it doesn't extend to
As opposed to the other side up in there, it's got an arrowhead, right?
Yeah.
Okay. You want to keep going with that?
It includes that point that nothing is
Good. So again, what's interesting about that point versus this arrowhead? What's the arrowhead do?
extends it to anything above.
Good. Keeps going further and further, also known as infinity. So again, back to the point. What's interesting about the point? Alan? Ooh. Okay, so hold on a second. I agree with you that it's a minimum, but how is this minimum different than Sam's minimum? Because Sam fired off this big max. I have no idea what just happened, but that was so cool. Okay, there, yeah, yeah, where were we? Okay, we're back to the picture. Sorry for that brief interruption. So how is your minimum different than Sam's minimum, or are they different? Or are they the same? Ooh. Area, if you will. The technical term is neighborhood. Right. So Sam's minimum is just the minimum in that neighborhood. You are talking about the minimum of the entire graph. Interesting. Okay, so where's the maximum of this graph? Infinity. Can you get to infinity? No.
Well, the maximum in the neighborhood.
Oh, I don't know. I didn't specify. Could you expand upon your
Well, if you say
question?
what is like the maximum in this set, like between -2 and 2 for the x or maximum y, then you could give a definitive answer.
But
the graph continues because of the arrowhead.
okay. So we have this thing in calculus, which I haven't talked about, called a neighborhood. And a neighborhood is a small portion of the graph. The question is, how small? There's no answer to that question. Now, the reason I didn't talk about this is because it involves a very, very formal definition of some of the things we've been doing, which involves deltas and epsilons. And if we went through that, many of your brains would just melt and run out your ears. So I skipped it. But you should understand the idea that small portions of the graph are commonly known as neighborhoods. You can adjust the size of that neighborhood. But if we just look at that neighborhood that I drew over there, then we have a maximum that Sam talked about earlier. If my neighborhood is the entire graph, that changes. Is there a maximum for the entire graph? You would say, yeah, it's infinity, but infinity doesn't count. Why doesn't infinity count? Because you can't get to infinity. I just keep going up and up and up and up, so I never reach that maximum value. Okay. With me so far? All right, now we get some terminology. Those absolute values are called absolute max and absolute min. It includes the entire graph. So if we look at this picture, our absolute min is that dot that we were talking about earlier. it has no absolute max. Every graph doesn't necessarily have an absolute max or absolute min. Okay, but again, you can write all that down. None of that matters. What you want to know is simply that. Where's the biggest value on the graph? Where's the smallest value on the graph? Those are the absolute maxes and mins. Sometimes sources will use the word global, which also means the same thing as absolute. So a global max and an absolute max are the same thing. Questions? Does that make sense? We're good? All right, good. If we start looking at neighborhoods, we get what's called a relative max and a relative min. Okay, these are the values that Sam talked about. In this little neighborhood over here, the max is right there. In this little neighborhood over here, the min is over here, commonly called a valley. As the title of the slide says, relative has a similar term or an analogous term called local. So local max and relative max are the same thing. Local min and relative min are the same thing. I don't know why there's so many terms for these things. I wish somebody would just pick one and go with it, but they don't. Some books use relative, some books use local. Sometimes the AP test uses relative, sometimes it uses local. So I'm just going to make sure that you've seen them all so they make sense. Okay, are you good with the difference between the two? Okay, absolute covers the entire graph, local just covers these little neighborhoods. I think it's easier if you think of it as like hills and valleys. We good? All right, so here's some example of some neighborhoods. Taking that graph and breaking it into those small little blue areas, we get a local min, a local max. And you'll notice that value at K is both a local and an absolute min. It can be both. Is it a low point or a valley in that neighborhood, and is it the low point over the entire curve? Five points that I'm interested in. A, B, C, D, and E. Let's start with D. Kate. Is the point at D an absolute max, an absolute min, a local max, and or a local min? It's not a good way to start an answer. Start over. It is a local max. Anything else? Absolute max. Anything else? Anything else? Say no, because that would be ridiculous. It can't be a max and a min at the same time. Okay. Everybody agree? D is the highest point on the entire graph. It's also the highest point in that little neighborhood. Let's give it up for Kate. Sarge. B, as in Badger. Absolute max, absolute min, local max, local min. That's it? Just local max? Outstanding. Let's give it up. Yeah. E as in elephant. That's it. Good. Give it up. One second. What have we done?
We haven't done C.
We haven't done A or C, right?
Correct.
Let's do C first. Akira. C as in cat.
Local min.
That's it?
Yeah.
Well done. By the way, notice how C comes to a corner there? Yeah? Where the other ones are nice smooth curves? We'll come back to that in a second, just wanted you to point that out. All right, let's deal with A. John, what's A? Both. Outstanding. Now, I don't clap yet. I would agree with him because I didn't give you all the information. A is just a local min. But you're saying to yourself, wait a minute, it's the lowest point on the graph. You are correct, but endpoints cannot be absolute, or sorry, let me say it again. Endpoints cannot be local extrema. They can't be relative max or relative mins. So A would only be an absolute min. One last thing on this slide. Let's change A to look like this. We already know it can't be a relative min because it's an endpoint. Is it still, and you kind of know the answer of where I'm going here, is it still an absolute min? Why not, Matt?
Because the point A doesn't exist. Like it's yeah, I guess it's like A doesn't exist. The min would be the point directly next to it.
Which we can't find.
Exactly.
Good. So that situation is very similar to the arrowhead we had on the red graph. You can't ever get to that value. We want A to be an absolute min, but you can never get there. You can get closer and closer and closer, but never reach it. Okay. That comes up most commonly when we talk about intervals. So we can talk about the interval from A to B, or we can talk about the interval from A to B. What's the difference between the two? Like,
Actually,
for which one?
the second.
The second does not count A and B.
No.
Correct. Okay. Brackets mean you include A and B. Parentheses mean you don't. So this, what we're looking at here would be something like whatever this point, let's call that Q. Okay. Problems? Hopefully not real difficult, yes? Okay, beautiful. So now we're going to move on to critical numbers. This requires quite a bit more algebra. Obviously, looking at pictures, not too bad. Where's the highest point? Where's the lowest point? Where are peaks and valleys or hills and valleys in a little graph? Critical numbers get a little bit more involved there. The picture on the left is what I wanted to talk about. That's called a cusp or a corner. It's when the graph makes a corner. Those kind of points are called non-differentiable points. You cannot take the derivative there. In other words, the derivative does not exist. We're going to be looking for two things in graphs. We're going to be looking for where the derivative equals 0, and we're going to be looking for where the derivative does not exist. How do I get a derivative that doesn't exist? We'll get to that later, but commonly on a graph, that's what it looks like. So if I go back to this guy, at the point C, we have a non-differentiable graph. Okay, it's a corner. We want to find these critical numbers, and 99% of chapter 4 involves finding these critical numbers. Because it's something that we're going to do a lot, we're going to take our time and make sure we know what we're doing. Now, why do we want the critical numbers? As it says there, the critical numbers are where the function, where the derivative equals 0 or where the derivative does not exist. And then famous mathematician Fermat said, well, let's go backwards. If the derivative doesn't exist, then that's going to give us a local max or a local min. We'll deal with Fermat later. What's more important right now is definition number 3. Okay? This is big. We're going to do it a lot. And in fact, most of the rest of the slideshow is just examples of doing just that. Okay? Good? Derivative equals 0, derivative does not exist. Okay, so find the critical numbers. Go ahead. Take the derivative, set it equal to 0, solve. I'll wait. How am I doing so far? Good? Okay, so now at this point you can think to yourself,
Wait.
right, good. I was just testing to see who's paying attention. I'm proud of you guys. You're my favorite class.
Thank you.
At this, shh, Liz, just keep going on what you're doing.
I said that last week.
At this point, you can decide how you want to handle this. I could pick up my handy dandy calculator, type it into the quadratic formula, and get my two answers of 3 and -2, or this would be an example of something that might not be on the calculator portion of the exam, so I would do something like this. Okay, but again, type in your calculator, whatever you prefer. Okay, now we need to talk about a couple things here. First of all, is this thing called the zero product rule. Ever heard of it? This is where you all say yes. Yeah, because I know you have. Very simply put, if A times B equals 0, what do you know? At least one of them is 0. Do we know which one? No, so what do we assume? They're both equal 0. This is the basis for solving a number of problems. Okay? Again, the zero product rule. But what happens is that people start getting creative. And they start making their own rules. I'll give you an example of one that I saw recently. I should get two answers, yes? Okay, so how would you solve it? That's kind of a silly question, but I'll show you why it's a silly question in a second. You move the 5 to the other side, set it equal to 0, factor it. If it doesn't factor, use quadratic, whatever, right? But what I see is this. That, in the industry, is what we call bad math. Don't do that. Okay? Some of you, unfortunately, have already done that. Stop it. Zero product rule means they have to be equal to 0 when you multiply them in order for that to work. Okay? Good? These two values that we found here at the bottom are then what's called our critical numbers. They make the derivative equal to 0. Notice my notation. I took the derivative, I set that derivative equal to 0, I factored out. You didn't have to factor. Again, you could just pick up your calculator if it's a quadratic and go from there. Any problems? That should be pretty easy, yes? Okay, good. Well, how could we make it more interesting? save that for the end. Remember that whole factoring out thing? Second to last example we'll bring that into play. We're going to talk now about how to find an absolute extrema. Where's the highest point in the graph? Where's the lowest point in the graph? Of those critical numbers, it is possible that one of those critical numbers could be the maximum. Okay, let's go back to this picture. Using your calculator or Desmos, graph that cubic, please. I could probably ask this question without having you graph it, but I'll have you graph it anyways. Does that function have an absolute max or an absolute min? Why are you furrowing your brows at me, Jack?
Since it goes infinitely in each direction.
Right. It goes infinitely in each direction, so the answer is no. It doesn't have an absolute max or an absolute min. But if I restrict it to an interval, now all of a sudden that changes, which is what we're going to do when we're solving for absolute extrema. Where's the highest point? Where's the lowest point? We have to know what we're talking about. There are the 4 steps to do it. Feel good? Sorry again. Okay. So let's look at this example. Now let's start with the quartic. But you'll also notice that I have an interval here. Step 1 is to find the critical numbers. Okay, I can do that. F prime of x is equal to 12x cubed minus 12x squared. Set it equal to 0, factor that out. Critical numbers and 1. Okay. Now, if you'll recall that red graph that we started at the bottom, or at the beginning of the slideshow, I should say, had some endpoints. This one has endpoints too. So I need to check, very simply, as I said before, an absolute max is the highest point in the graph. I know that the only high points of the graph can happen either at a critical number or at one of the endpoints. So I'm going to go to the old Algebra 1 T-chart. Notice I'm plugging into f of x, not f prime of x. And I'm going to check 4 points. -1, 0, 1, and 2. Okay. -1 and 2 because they're the endpoints of the interval, 0 and 1 because they're my critical numbers. Now I showed you, I think last block of the block before, how to quickly find values of graphs. You could plug it into y1 and look at the chart, or the table, I mean, not the chart, the table. Or you can use the method I showed you on the home screen. For now, I would just use the table. Put 3x to the 4th minus 4x cubed into y1, go to the table, and generate a bunch of values. Scroll up and down, find these values, and then share those values with me for an answer of, or answers of,
7.
7, good. I can do 0, 0. -1.
16.
And how much?
16.
16.
No, that was
By the way, I had them on the next slide. They're right there. Okay, but that's okay.
it's
Again, this isn't rocket science. Now I ask myself a simple question. Where's the biggest value? Okay, so let's talk about semantics, because the College Board loves to do this. They will ask you, where does the max occur? Sorry, where does the absolute max occur? The answer to that would be 2, 16. They will ask you, what's the x value of the absolute max? That would be 2. Or they will ask you, what's the y value, or, sorry, they won't say that. They'll say, what is the absolute max value? That would be 16. So this is x value of absolute max This is the absolute max value. And then we've got a min there. Absolute min. I don't care anything else about what that graph does. I don't care what it looks like. I don't care what shape it is. I just care about the biggest value and the smallest value. Problems. Make sense? Yes? Good. Okay, so yeah, I did a fancy graph. Okay, you do one now.
I got 3. Two of them are discrete.
How do you solve?
So you have your derivative,
Yeah.
and then you
Oh, factor out next. I didn't know algebra. Fun.
48 plus 12.
Yeah.
36 divided by 4. 9.
Oh, you factored out. Oh, you smart man.
I'm trying.
Oh wait, no, that's too much work.
The one I just gave you.
Annoying.
What?
Oh, no.
Yeah, did you get like
No,
take this back.
11.196?
Yeah. Ever since I was a kid, my dad, sensitive to it, and I find myself doing it to other people, and it bothers me to bring things out of people's hands. It's so rude.
I don't think we need to find f of 11.96, because that's not on
It's
our
not in
interval
the-
of -1 to 4. So that's fine.
Okay.
Are these 3 your critical numbers?
For critical numbers, get 11.
11 something, 28 something, 0.
Alright, try that, Hoss. Okay, there's something wrong with the calculator. Sorry, did it again. You guys see that, Sam? Thanks. When did it show?
This last.
Wait, what do you got to find your critical numbers to get into chart on that?
For the .80 ones, I guess, and I'm just gonna plug it.
That's fine.
This one is just kind of.
Let me look at it later.
Oh,
Alright, talk to me. How many critical numbers did you find?
Do you plug it into the original function?
3. And by the way, 2 of them are ugly, yes?
Yeah.
Okay, so I did that for a reason. Number 1, to instill the idea in you that this is calculus and not every answer is -1 or 3. The critical numbers were x equals 0, 11.196 and 0.804. What's it again? 804, thank you. So, put them on a T-chart. X, f of x, 0, oh no, not 0, -1, 0, 0.804, 4, and 11.196. Now, these two weird numbers, 0.804 and 11.196, won't show up if you use the table method. There's two ways around that. You could change your table setting to ask for the number, or you can use the home screen method that I showed you where you store the number into X and then type the function out. Okay. So, we get some answers here. When I plug -1 in, I get 35. When I plug 0 in, I get 0. Did that one without a calculator. 0.804? Close enough. 4? I'm sorry, -480? Ooh, that's a big number. And 11.196 is going to be even bigger. Kelsey?
Do we have to look at it? It's outside of the image.
Oh, very nice. Everybody catch that?
No.
That goes away. Why, Kels?
It's not in the interval.
It's not in the interval. We're only looking at numbers from -1 to 4, which is also why I included it. Okay, it goes away. We don't care what the value is. Okay, again, keep it simple. Where's the max? Where's the absolute max? -1, 35. Where's the absolute min? -4, -480. Good. Whoops, 80. Okay, easy. How are we doing so far? Okay? Not bad? Yeah? Simple polynomials, taking derivatives and setting them equal to 0. Fun. Okay. This is going to be fun. So remember that whole business about simplifying derivatives? Well, it's just come to visit. Go ahead. You have the answers, by the way. They won't help, but go ahead. Let's review the process. Take the derivative, set equals 0, solve. Whatever you want to dive right in there. Go ahead. Start taking that derivative. Sometime today.
Is this a product
Yes.
with a chain with a particle?
Yes.
No. What?
Where do you see the second product rule?
So you have to because these two multiply together. And you chain
No.
these.
You have to chain that. You didn't chain these right. You didn't chain them right.
No, I didn't chain them yet. Wait, I'm trying to simplify that cubic. Jesus Christ. Okay, if I do.
Oh God.
I literally do not know.
Anybody crying yet?
Yes.
Yeah.
Okay.
Yeah, but
I know that.
yeah. Oh, it actually gets easier.
Actually, it's not that bad. Which one did you do first? You might like the same time. I'm not sure. It's like a whole product rule. So like x plus 7 squared times the derivative of this, which is what you know. And then plus q through x minus 8 times the derivative of this, which is g.
Oh,
That's not actually lost.
no. And then
Actually, I'm so lost. Please get my name right.
Yeah.
Yes.
What's the sign say?
Which one?
Under the clock, what's the sign say?
I wasn't whining. I was clarifying it dumb because you got my name wrong. It's different. Oh, I'm sorry. Dumb.
Thank you so much. I appreciate it. To making sure you pronounce my name correct. You're so welcome.
Okay, so that's enough time for some of you to get to the point of frustration, which is exactly where I wanted you to be.
Where is no, wait, that's 8 to the no, wow.
I'm assuming that you all got there.
Yes.
Yeah.
Beautiful. This was not a practice on product rule. Because by now, you should be Zen masters when it comes to product rule. This is an example of how to simplify, because we're going to set that bad boy equal to 0 and solve it. But there's a problem. The problem is that little plus sign. Plus sign, bad. Multiplication sign, good. So I need to figure out how to turn a sum into a product. To do that, I'm going to factor stuff out. You'll notice, just for discussion purposes, we're going to call that the blue term, and we'll call this the black term. The blue term and the black term have common things between them. What are the common things? X plus 7 and x minus 8. Beautiful. I'm going to factor those out, and this is what's new, because I don't think we've talked about this yet. That's important. I can either factor out an x plus 7 or an x plus 7 squared. I can either factor out an x minus 8 to the 1/3, or I can factor out an x minus 8 to the negative 2/3. The rule is very simple. Always, without exceptions, take the smaller exponent. So, x minus 7 or x minus 7 squared, I'm going to take the x minus 7 to the first power. X minus 8 to the 1/3 power, or x minus 8 to the negative 2/3, I'm going to take the negative 2/3 power. Then the stuff in the bracket is just all the stuff that's left behind. So from the blue term, I'm leaving a 2 behind, and I'm leaving an x minus 8 to the first power. Does everybody see why that's to the first power? Speak now or forever hold your peace.
Not
No.
really.
Okay. So, let's suppose I have that polynomial. If I factor out an x squared, you all are smart enough to realize I leave that behind, yes? Okay. Well, what am I actually doing? I'm dividing. I'm taking x squared, dividing it by x squared, and getting 1. I'm taking x cubed and dividing it by x squared and leaving x. I'm subtracting exponents. Okay, now knowing that, when I subtract exponents, I have x minus 8 to the 1/3 power, and I'm factoring out to the negative 2/3, so I have 1/3 minus negative 2/3, which is a nice pretty answer of 1. Then the black term, what do I leave behind there? I left behind a 1/3 and an x plus 7. That makes me happy. Why does that make me happy? Because now I have a whole bunch of multiplication. Two things multiply together to give you 0, they both must equal 0. Three things multiply together to give you 0, all three of them have to equal 0. X plus 7 equals 0. X minus 8 to the negative 2/3 equals 0. And 2x minus 16 plus 1/3 x plus 7/3 is equal to 0. Okay, so let me put the answers up there. Okay, let me put the answers up there. Good. So the -7, no problem. I'm assuming the 41/7, even though it's an ugly answer, I'm assuming you could find that. Okay, because this gives me the 41/7. This gives me the -7. Let's talk about this guy, however. So you'll recall in the beginning of the slideshow, I talked about critical numbers being where the derivative is equal to 0 or where the derivative is undefined. That x minus 8 is a little wonky because if I rewrite it, this is the same thing as 1 over x minus 8 to the 2/3, or if you prefer, 1 over x minus 8 squared and then take the cubic root of that. Either one, it's the same thing. But that 8 value is not going to make it equal to 0, it's going to make it undefined, which is fine. It doesn't matter because we want where it's equal to 0 and where it's undefined. So this idea of factoring things out in common and taking the smallest exponent pops up over and over and over again. Right now it might be a little overwhelming. In a week or two, you're going to do this in your sleep. It's just going to be so simple, you're not even going to have to think about it. But it does take a little bit of time to get there. Questions? Okay. Now, where are we going to from here? What we're going to do is then learn a little bit more about what those critical numbers represent as it relates back to the graph. And start doing a whole bunch of things like first derivative test, second derivative test, et cetera, et cetera. I got one last example for you that involves the Hubble Space Telescope. This is a type of problem you will see on the AP test. They like word problems. The Hubble Space Telescope was deployed on April 24th, 1990. Who cares? By the space station, by the Space Shuttle Discovery. Also, nobody cares. The model for the velocity of the shuttle during this mission from liftoff at time t equals 0 until the solid rocket boosters were jettisoned at t equals 126 is given by that ugly equation. Using this model, estimate the absolute maximum and minimum values of the acceleration of the shuttle between liftoff and jettison of the boosters. Okay, so let's talk about that a little bit. If I give you the velocity, how do you get the acceleration? Take the derivative. Okay, that's not a problem. We got that. But notice what the question is asking. Where are the absolute max and mins of the acceleration? So I actually then have to take the derivative of the acceleration in order to take the max and min. So forget about this space telescope problem. Just think about what we did in the very beginning. How do you find an absolute max and min? You take the derivative of whatever the function is, you find the critical numbers, and you test the critical numbers with the endpoints. What are the endpoints for this function?
0 to 126.
Good, 0 to 126. My interval here, when I get down to it, would be 0 to 126. Take the derivative of the velocity to get the acceleration, then take the derivative of the acceleration. Trivia question, anybody know what the the derivative of the acceleration is called?
Jerk.
It is called the jerk. Set that jerk equal to 0. solve for critical numbers, test the critical numbers, and test the endpoints of the interval. Okay. I'm not going to take you through that problem. It's got some ugly decimal values, and that the solving the problem is not important. It's the concepts behind the problem is why I included it there. The idea of taking whatever function you're talking about, in this case the acceleration, taking its derivative to find the absolute max and min. Okay, we good? All right. Anybody?
Oh, it's in these seven.
Hmm? What kind of Nissan?
A sedan.
Kind of sedan. Oh, it is.
Oh, I know that.
I was.
I thought
And what's on the left?
Family maximum.
Family maximum.
Yeah, makes sense. I don't know.
What was that, Luca?
Relatives.
John? Yeah, those are relatives.
Oh.
It's a family. They're relatives. Get it?
So
Relative maximum. Relative. You guys.
Middle class sports.
This is a rough crowd.
I like it.
No?
It's clever.
Oh, thanks.
I like things here.
I'm gonna have to test your comedy chops a little bit. This didn't go so well.
Honestly, I just thought it was a Liam Neeson joke. Middle class sports.